So in Audacity here, I've recorded the sound of a tin whistle as an example. So there was this on the top one, then middle one, and then finally in the third one. So this is with the same length of a tube, and we get three very different sounds. So let's just zoom in and see the difference in the patterns. So in the top example, which was the lowest note, let's see, we could measure the time for 10 of these main waveforms. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that gives a time down here of 0.016861. 0.016861. We notice that within that waveform there are 1, 2, 3, 4 smaller waves. So there would be a frequency 4 times the one we will find for the main pattern. In the second example, let's zoom in a little further. Again, we can take the main pattern, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 waves, and the time is 0.008410, which is approximately half the time for the one above. Now again, if we take the peaks, there's 1, 2, let's see, there are, from the peak to the next peak, there's 1, 2, 3 waveforms. Now in the bottom one, again, we can take the time for 10 waves. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this time we have a time of 0.005274. So let's do a quick calculation. If we have 0.016861 divided by 10 to get the time for one wave, and then invert to get the frequency, that comes up as 593 Hertz. Alternatively, we had the 0.08410 time for 10, so divided by 10 to get the time for 1, invert, and we have 1189 Hertz. Now if we divide that by 2, we get 594. So the frequency of the second example is twice that of the first. Let's look at the third. The third time was 0.005274 divided by 10 to get the time for one wave, and invert to get the frequency, which is 1896. Now this one doesn't have such a simple relationship to the 593. Let's see, 593. No, there isn't really a simple relationship between them. This kind of exploration is simple and easy to do in Audacity, even with such a simple little instrument as a tin whistle.